In the last video, we found that absolute extrema, that is absolute maximums and minimums, happen either at the endpoints of an interval or where the derivative is 0 or undefined. And so these are the places that we're going to go looking whenever we get together on Zoom again for absolute maximums and absolute minimums. We said that those last two bullet points are what we're going to call the critical points of a function, places where the derivative is either equal to 0 or undefined, and that we were going to continue to use critical points throughout the rest of the chapter. So here's our official definition of a critical point. We say let C be in the domain of f of x. We say C is a critical point of f if either the derivative is equal to 0 or is undefined at x equals c. First of all, just to get used to the definition, we're going to identify some critical points on this graph here. All right, so let's look for places where the derivative is equal to 0. These are going to be places where the tangent line goes completely horizontal. And I only see two of them here, and sort of helpfully drawn there are these dotted horizontal lines. So I see one over here at x equals 6, and then at x equals 0. Kind of looks like part of an x cubed graph there, where it just flattens off ever so briefly on the y-axis and then continues to increase. All right, so we're going to say we have critical points at x equals -6 and x equals 0. And critical points I've always felt is a weird word to call these things. We usually just report the x coordinate of these points. We don't report them as ordered pairs, which is something that usually you would do for something you're calling a point. But this is kind of a term that we're stuck with and a convention, a way to represent them. So a critical point, we just refer to the x coordinate. The other place where we might have a critical point is where the derivative would be undefined. So we know that the derivative is undefined when we get to corners or cusps, and we have two of those on this graph. I've got one here at x equals -3 and another one at x equals +2. So those are also going to be critical points. So we're going to say x equals -3, x equals 2. A very uncommon kind of undefined derivative spot is over, it looks like at 7.5. And that's the place where this tangent line briefly goes completely vertical. So remember, the derivative is the slope of the tangent line. Vertical lines have undefined slope. So a place where the tangent line is vertical is going to have an undefined derivative. So we're also going to say there's a critical point at x equals 7.5. Kind of have to guess that it's right there exactly between 7 and 8. So notice that these critical points are not necessarily absolute maximum or minimum spots. You get to be a critical point by having the derivative equal to 0 or undefined at your place on the graph. It doesn't necessarily mean that you're a max or a min. We're going to have to learn how to test these critical points to see if they give rise to an absolute max or an absolute min. So let's actually find some critical points. So we have a function f of x equals x cubed plus x squared minus x, and we want to find all the critical points. So critical points are where the derivative is 0 or undefined. So let's find the derivative. So f prime of x is going to be pretty easy on this one. We're going to take power rule, 3x squared plus 2x minus 1. This one is not going to have any critical points from being undefined. There's no number that I can't plug into a quadratic function. I can plug in any number I feel like. So this one is always defined. We're only going to find critical points where this derivative is equal to 0. So we're going to set this equal to 0. And we're going to have to remember how to factor a quadratic. You also could use the quadratic formula if you abhor factoring. That will also give you the right solution. So however you factor, we're going to need a 3x and an x. Let's see, I need the numbers to multiply to give me -1. So it's going to have to be 1 times 1. And then I just have to decide if I want positives or negatives in the middle. And I'm going to need a positive over here and a negative over here. And again, that's just so that when I do my FOIL, my outer terms and my inner terms combine to give me that plus 2x in the middle. All right, so now we've got it factored, we're going to take both factors and set them equal to 0. So 3x minus 1 equals 0. X plus 1 equals 0, and then solve for x. So I'm going to add 1 to both sides over here, and I get 3x equals 1, divide by 3, and I get x equals 1/3. So I'm going to write that over here, my final answer pile. X equals 1/3, and then we're going to get an answer for our second factor, subtract 1 from both sides, and we get x equals -1. So those are our two critical points. And again, that's not guaranteeing that I'm going to have an absolute maximum or minimum at either one of them. Those are just the only candidates that we get from critical points. All right, one more function. We're going to find all the critical points for f of x equals cube root of x squared minus x. I know I'm going to take the derivative and set it equal to 0 or figure out where it's undefined. So if I'm going to take a derivative of this, I need to convert that root to an exponent. So let's rewrite this as x squared minus x. to the 1/3. And I know I'm going to need a chain rule here because I've got an inside function, x squared minus x, and I've got an outside function, the 1/3 exponent. So I'm going to come over here and find my derivative. Derivative says take the derivative of the outside function. So we're going to bring down the 1/3 and subtract 1 from the exponent. So if you need to, go off into your scratch work and say, what's 1/3 minus 1? That's going to be 1/3 minus 3/3, or negative 2/3. So that's my new exponent, negative 2/3. So that's the derivative of the outside function. Leave the inside function alone. So leave the x squared minus x alone. Then we multiply by the derivative of the inside function. So the derivative of x squared minus x is 2x minus 1. All right, and so I need to set that mess equal to 0 or figure out where it's undefined. I definitely want to do some simplifying before I think about that because that looks like a mess. So I'm going to take the thing with the negative exponent and go ahead and move it down to the denominator with the 3, and then we'll see where we can go from there. All right, so down in the denominator, I'm going to have the 3 for the 1/3 fraction and x squared minus x to the 2/3. And then all that's left in that derivative is 2x minus 1. That's going to stay up top because it had a positive understood exponent of 1. All right, so I need to figure out where the derivative is 0. And I also do need to think about where the derivative might be undefined for this one because we have a denominator, so we might have it be undefined somewhere. All right, so where the derivative is equal to 0, let's think about that first. So where is f prime of x equal to 0? All right, that's going to happen where the numerator of the fraction is equal to 0. If I can figure out what makes the top equal to 0, 0 divided by whatever is going to be equal to 0. So we're going to take that numerator and just set it equal to 0. 2x minus 1 equals to 0, and that'll give us a critical point. So I'm going to add 1 to both sides, and I get 2x equals 1. Divide both sides by 2. And I get x equals 1/2. So I'm going to come over here on the right and start making my pile of critical points. X equals 1/2 is my first one. And then I'm going to have more to come from where this derivative is undefined. So the derivative is going to be undefined at any x value that causes division by 0. So this is kind of like looking at the domain of a rational function. We're going to figure out what makes that denominator equal to 0. And so now we're going to look at the denominator equal to 0. So f prime of x undefined. We're going to set 3 x squared minus x to the 2/3 equal to 0. All right, first of all, that 3 is not going to be equal to 0. We can just kind of divide both sides by 3, get rid of that, which leaves me with x squared minus x to the 2/3 equal to 0. So now what are we going to do with this to solve for x? I've got a set of parentheses raised to the 2/3. The trick we need, and this is not necessarily one that you run into in your average pre-calc background, the trick we need is to raise this to the reciprocal power. So we're going to raise it to the 3/2 power. So I'm going to raise both sides to the 3/2. And what that does, you multiply. When you have an exponent to an exponent, you multiply the exponents. So I'm going to multiply 2/3 times 3/2. And that gives me a 1. So you basically end up with just a 1 exponent. You've canceled out the exponent. Technically, you've been doing this for years without realizing it. When you solve an equation with an x squared in it and you apply a square root, remember the square root is the 1/2 exponent. You're kind of raising that square to the reciprocal power. So once we raise that 2/3 to the 3/2, we just have left the x squared minus x equals 0. Another quadratic. Don't divide both sides by x, because if you do, you lose one of your answers. So factor out an x, and you end up with x minus 1. And then set both factors equal to 0. So I set x equal to 0 and x minus 1 equal to 0. X equals 0 is one of our critical points. I'm going to add that to my list up here. And then for x minus 1, we just add 1 to both sides, and I get x equals 1. So that'll be my third critical point. So this function had a lot of critical points all kind of crammed together there in between 0 and 1. Now that we know how to find critical points, we'll be able to test all those critical points to see if they might be the absolute max or the absolute min of a function. We'll do that when we meet together in Zoom.